In this video, we'll explore Arm's Scalable Matrix Extension. First, we'll recap what we mean by matrix multiplication. Then we'll look at the SME hardware. And finally, we'll write some Arm assembly code to implement matrix multiplication on SME. Let's start by recapping what we mean by matrix multiplication. A matrix is an array of values. If matrix A has m rows and k columns, and matrix B has k rows and n columns, then the result of the multiplication will be a matrix C that has m rows and n columns. Each element of C is calculated by summing the products of pairs of elements, drawn from the corresponding row of A and the corresponding column of B. As you can see, that's a lot of multiplies, even for a small matrix. Let's look at the SME hardware. There are 32 Z registers named Z0 to Z31 and a square tile array named ZA. The width of the Z registers and ZA tile is determined by the scalable vector length, which is implementation specific and is a power of 2 from 128 to 2048 inclusive. For a vector length of 256 bits, the width would be 32 bytes and the ZA tile would be 32 rows high. For a vector length of 512 bits, the width would be 64 bytes and the ZA tile would be 64 rows high. Let's look at the case where SVL is 128 bits. The ZA storage is 16 bytes wide and 16 rows high. So when accessing byte-size elements, it forms a single square tile, as shown by the grey diagonal called ZA0.B. When the ZA tile is accessed as 16-bit half-words, there are 8 half-words per row. That means that a square tile would be 8 rows high. Because of this, the ZA storage can host two 16-bit tiles named ZA0.H and ZA1.H. These virtual ZA tiles are actually interleaved in the physical ZA storage. Similarly, when the ZA tile is referenced as 32-bit words, there are 4 words per row. So a square tile would be 4 rows high. This means the ZA storage can host 4 32-bit tiles named ZA0.S through ZA3.S. As before, the virtual ZA tiles are interleaved in the physical ZA storage. This pattern continues for 64-bit double words. The 8 64-bit tiles are named ZA0.D through ZA7.D, and of course they are interleaved in the physical ZA storage. For 128-bit quad words, there are 16 tiles named ZA0.Q through ZA15.Q, and are each a single cell in size. Bear in mind that for implementations with vector length greater than 128 bits, their dimension would be larger. Returning to byte access, let's look at how the ZA tile is populated. First, we load the memory contents into a Z register. Then we can move the Z register into a row of the tile called a tile slice. The H means that we are accessing a horizontal tile slice. The B means that we are accessing byte-sized elements. If W12 is 0, then W12 plus 5 selects row 5 of the tile. We can also load data into columns in the ZA tile. The V means that we are accessing a vertical tile slice. This time the value of W12 is 4, so W12 plus 5 selects column 9 of the tile. We can also move data back from the ZA tile into Z registers, and from there, back into the memory. But what if our matrix is not an exact multiple of the ZA tile size? In the previous load instruction, you may have noticed the P3. This is a predicate register and acts as a mask. The /Z means that inactive elements are set to 0 in the destination Z register. For a tile slice move instruction, the /M means that inactive elements in the destination tile slice remain unmodified. The same is true when accessing a vertical tile slice. We can use predicate registers when moving data out of the tile too. When storing to memory, there is no /m or /z. Inactive elements are not written to memory. Now let's look at 32-bit word access to the ZA tile. In this example, we will load 4 Z registers in one instruction. Notice the PN9 here. This is the same register as P9, but the N means that it is treated as a counter instead of a mask. More on this later. Now we can fill 4 rows of the ZA tile at once. The S means that we are accessing 32-bit word-sized elements. Recall that tiles are interleaved in the ZA storage. Let's see 32-bit words being loaded into columns in the ZA tile. Notice that for element sizes greater than 1 byte, the V syntax does not select full columns in the ZA storage. Instead, this example selects full columns in the ZA2 tile. Let's focus on the ZA0 tile and take a look at the matrix outer product instructions. The FMOPA instruction performs a floating point matrix outer product with accumulate. The product of each row of Z0 and each column of Z1 is added to the existing value in the tile. The P2 and P3 predicate registers control which elements are active. Notice that where the predicate is inactive, the value of the tile is not modified. Let's look at the result if the tile had been zeroed first. The ZA tile and Z registers are indexed with column 0 on the right, but for the rest of this video we'll show them mirrored to better resemble the way people write matrices. Recall what the product of matrix multiplication looks like. Right now, the Z registers contain the values highlighted red. The resulting outer product matches the portion of the result matrix highlighted red. By performing outer product operations on additional rows and columns, we can construct the missing parts. Recall that the FMOPA instruction accumulates, but for clarity, the top right matrix only shows the values calculated from each pair of Z registers and not the accumulated totals. So far, we have calculated the first 16 values of the result in the ZA0 tile. But since we are dealing with 32-bit values, there are 3 additional tiles available, so let's make use of them by operating on different elements from the source matrices. It is far more efficient to load data from contiguous addresses in memory, so let's rearrange the left matrix A. We can efficiently generate each quadrant from the highlighted source values. Now we'll need some Z registers and some predicate registers. We'll extract the predicate registers from predicate-as-counter registers PN8 and PN9. More on this later. Let's take a look at some code. First we load the k=1 values for the top tiles from an address pointed to by x7. Next we load the values for the left and right tiles. Since we're loading multiple registers, this is governed by a predicate-as-counter register. Finally, we load the values for the bottom tiles. Now that's done, we can calculate the contribution of these values to the result, shown as a red dot in each result cell. Recall the result we're trying to calculate. The red terms in this matrix correspond to the red dots shown in the ZA0 tile. It's actually better to interleave memory access and data processing instructions in order to minimize pipeline stalls. Notice that whilst we're loading 2 values at once from B, we're only loading 1 value at a time from A, and it would be more efficient to load 2 each time. However, we would then need to load 4 values from B in each loop iteration, so we'll need to unroll the loop on K so that it processes 2 values of K for each iteration. To do this, we'll need to use a second set of Z registers. First we add the vector length to x7, so that it addresses the next line of A. Now we load 2 sets of K values for the top tiles. Next we load the values for the left and right tiles. As before, it's best to calculate the first outer product now. Next we load 2 sets of K values for the bottom tiles. And finally we can calculate outer products for the remaining quadrants. what if we're at the bottom of the A matrix, and there are active rows in the top quadrants, but none in the bottom quadrants? We can take care of this with a predicate select instruction. Our initialisation code will set PN10 to all true, which means that we will always load 4 rows of matrix A data for the top quadrants. We will arrange for W14 to be 0, so the pCell instruction tests the first element of P3. If active, it sets PN11 to the value of PN10, which is all true. Otherwise, if inactive, it sets PN11 to all false. This means that we will load 4 rows of matrix A data for the bottom quadrants, but only if at least one row in the bottom quadrants is active. Otherwise, we don't load anything. Now we can interleave the 2 loops for better pipelining efficiency. We'll need to do some loop housekeeping. First, we increment x17 by 2 rows of B. x2 equals n, so shifting it left by 3 gives 2 rows times n elements times the 4 byte element size. Next, we increment x7 by 2 times the vector length. Since each row of A has width equal to the vector length, this increments x7 by 2 rows of A. Now we can test whether we have finished our loop on K by comparing x7 with x15, which points to the last of the K rows in matrix A. If x7 is smaller, then we branch to loop K. But where should we place the loop K label that we will branch to? Since we're loading 2 rows of A now, we don't want to include the single loads or the single row increment of x7. By placing loop K here, we have excluded the first load from B and the first ZA0 outer product calculation, so we need to add them back in at the end of the loop. Let's reorder the instructions to improve pipelining. Now we can execute those 2 new instructions to complete the loop. Let's have another quick look at the ZA0 tile to check on our progress so far. x7 is less than x15, so let's quickly run through the next loop. Here we are back at the loop condition, and this time x7 is not less than x15, so we won't branch. We have only calculated the outer product for one quadrant of our final loop, so we need to finish that job. Let's take another quick look at the ZA0 tile. Great, we have calculated all the terms. But what if the k dimension were an even number? In this scenario, we haven't processed the data for k equals 6. Let's deal with that now. We compare x7 with the x8 register that we will have initialised to point to the next block of k. x7 is not greater than or equal to x8, so we continue. Returning to the scenario where k is odd, we would see that x7 is greater than or equal to x8, so we would have branched ahead to k tail end and skipped the additional processing for even k. By this point, we have correctly calculated 4 tiles of result data, regardless of whether k was odd or even. The next step is to write the tile data back to memory. Recall that when accessing elements of size greater than 8 bits, the ZA tiles are interleaved in the physical ZA storage. It's most efficient if we can write data to memory contiguously, so we'll want to write each row of ZA0 with its companion row in ZA1, and similarly for rows in ZA2 and ZA3. Notice that due to interleaving, the first rows of each ZA tile are contiguous in the physical storage. It's easy to extract these 4 rows into Z registers if we access a tile as bite-sized elements, since they are not interleaved. Similarly, we can access row 2 of each tile as contiguous byte elements, and so on for rows 3 and 4. The algorithm then will be to extract the same row from each tile into Z registers and write those rows to the output buffer in the correct sequence. Let's put this into practice. First we'll set W13 to 0. W13 is an alias for the lower 32 bits of X13. The PN9 register tells us which columns are active. This instruction tests a first row of P2, and if that row is active, then it sets PN11 to reflect the PN9 active columns, otherwise sets PN11 to all false. This instruction does the same for the bottom tiles, initializing PN12 based on whether the first row of P3 is active. Now we move 4 rows from the ZA storage into Z registers. Next we'll write 2 rows of data to X10, which points to our output buffer. The output buffer is n columns wide. The next row of data should be written SVLS rows down, which is SVLS times n elements. We'll use X23 to hold this quantity. We now write the next 2 rows to X10 plus SVLS times n, times the 4 byte element size. Now let's similarly process the second row of each tile. Notice the P-cell instructions use byte element size with offset 4, while the MOV-A instruction references rows 4 to 7. Using byte access for the P-cell means that W13 works as an index for both the P-cell and MOV-A instructions. We will need 2 additional registers to index rows 2 and 6 of the output memory buffer. X2 will hold n, while X18 will hold n times SVLS plus 1. Next we need to update the X10 pointer and the W13 loop counter. X2 holds n, so shifting it left by 3 means that we increment X10 by 2 rows, times n elements per row times the 4 byte element size. We add 8 to the W13 loop counter so that we can index the next 8 horizontal tile slices of the ZA storage, which map to the 3rd and 4th rows of the ZA0 to ZA3 tiles. We could at this point test W13 to see whether we have finished writing all the rows, and if not, branch back to continue storing rows to memory. But this approach means that in the final loop, we increment X10 and W13 unnecessarily. We can do better than this. Let's move the loop label to the point after we process the first row, and insert new code to process the 3rd row of each tile. Now we can test W13, but the trick is to initialize W6 to be SVLB minus 8. This means that when the loop condition is not met, there were 2 rows still to process when W13 was last updated. Since then, we have processed one of those rows, so there is now just one last row left to store to memory. Let's do that now. Great, we have calculated 4 tiles of result data and stored it to the result buffer. All that remains is to add loop code over the m and n dimensions and to initialize the registers that we have relied on. We'll need to set up the x7, x17 and x10 pointers, and we'll need to set x14 to 0 since we used it in this predicate select instruction. We don't need to worry about x13 because we have already initialized it. Similarly, x2 is an input parameter that will be passed in to our function. Let's look at a large matrix. We start with pointers x3, x4 and x5. After executing the inner loop on k, we have written 4 tiles to the output buffer. We'll need new pointers x9 and x16 to track the horizontal position of our working data so that we can avoid corrupting x4 and x5. Now we can advance x3 and x5 and reinitialize the horizontal pointers. Modifying x3 and x5 is okay, since we will not need to refer to their original values again. The P0 and P1 predicate registers mask off inactive columns. Similarly, the P2 and P3 predicate registers mask off inactive rows. To generate the predicates, we'll use the while lt instruction, which starts at the first operand, x16 in this example, and identifies all values less than the second operand, x11, within 2 tiles of bite-sized elements. Here, x11 is greater than x16 by more than 2 tiles, so the destination register, PN9, is set to a special value that signifies all true. We can extract the predicate-as-counter PN9 into 2 predicate-as-mask registers using the prext instruction. Predicate registers have size SVL divided by 8. For SVL of 128 bits, predicate registers are 16 bits in size. With byte encoding, each bit in the predicate registers represents whether a byte element is active. Since PN9 is all true, every bit in P0 and P1 is set to true. If x11 is less than or equal to x16, then PN9 is set to a special value that signifies all false. Where x11 is greater than x16 but less than 2 tiles ahead, then PN9 encodes the number of active elements. Skipping ahead, once we have more than 16 active elements, the second mask, register P1, starts to fill up. When we have 32 or more active elements, the PN9 counter is set to all true. The while lt instruction can also generate predicate counts for 4 tiles at a time. The prext instruction only extracts 2 predicate masks, which is why it takes an immediate operand. A value of 0 specifies it should extract masks for the first 2 tiles, while a value of 1 extracts the last 2. Let's look at how this works for 32-bit word-sized elements. This time, the while lt instruction starts at x12 and identifies all values less than x0 within 2 tiles of word-sized elements. With x0 less than or equal to x12, the destination register, PN8, is all false, and each bit in the corresponding mask register is 0. When x0 is greater than x12, PN8 contains the number of active elements. When we have 8 or more active elements, the PN8 counter is set to all true. For word encoding, each group of 4 bits in a predicate mask register represents a word element. An element is considered active if the least significant bit in its group is set. Now we'll return to showing predicate registers mirrored left to right. Let's look at some code. We have just finished executing the inner loop on k. Now we increase x9 by 2 times the vector length in bytes. We do the same for x16. Next we'll set the PN9 predicate-as-counter register using a while lt instruction. The x11 register must be initialised to x4 plus n times 4 bytes. The while LT sets the condition flags, so b.first checks whether there is at least one active element, and if so, branches to loop n. Let's look at the start of loop n. First we set x7 to x3, then x17 to x16, and x10 to x9. Now we can remove x7, x17 and x10 from our list of registers to initialise. Next, we extract the PN9 counter into P0 and P1 predicate masks. Now we're almost ready to go straight into the loop on K, but there is something very important that we haven't done yet, which is to zero the ZA tile each time we start the loop on K. Now we can execute the inner loop again, and this time, when we calculate the predicate counter PN9, the result is all false, because x16 is not less than x11. As a result, the b.first instruction is not taken, so we continue. We increment x3 by 2 k rows of SVLS elements. Then we increment x5 by 2 SVLS rows of n elements. Next, we increment x12 by 2 times SVLS. x12 will be our loop counter in the M direction, and our initialisation code will need to set it to 0. Now we set the PN8 Predicate-as-counter register using a while LT instruction. The x0 register is an input parameter that holds the value m. As before, the while LT sets the condition flags. PN8 contains active elements, so b.first branches to the start of loop m. Here we extract the PN8 counter into P2 and P3 predicate masks. Then we initialise x16 to x4 and x9 to x5. Next we set up x8, which the inner loop tests when handling even k, and x15, which is the exit criteria for the inner loop on k. We set up the PN9 counter at the end of loop n, which means that we still need to do it now for the first iteration. Now we just need to initialise the registers that we have depended on. We don't need to worry about x8 or x15, since we have just dealt with them in the loop m code. We can remove PN9, P0 and P1 from our list, since we have already taken care of them. Let's finish the initialisation code now. First we set a temporary register to SVLS. Now we initialise x22 to be k times SVLS, and x23 to n times SVLS. Now we can set x18 to n times SVLS plus 1. We set x11 to the right matrix address plus n times the element size. x12 we just set to 0. Next we set x6 to SVLB and x14 to 0. We set PN10 to all true. We previously set up the PN8 counter at the end of loop m, which means that we still need to do it now for the first iteration. Now we can remove PN8, P2 and P3 from our list. Finally, we subtract 8 from x6 to get its required value. We're almost done now. We need to save to the stack any registers in the range x19 and above that we have corrupted. For this function, that means x22 and x23. And we have to execute an SM start instruction that enters streaming SVE mode and enables a ZA storage. Similarly, at the end we need to issue an SM stop to exit streaming SVE mode and disable the ZA storage. And we need to restore the registers x22 and x23 that we saved previously. Finally, we return from the function. Earlier, we looked at how it is more efficient to load data from contiguous addresses in memory by rearranging the left matrix. The best solution is to arrange for the left matrix data to be stored in column major order from the outset. If that is not possible, then it will need to be pre-processed. Let's take a brief look at that now. Without going into too much detail on the loop code, we will process horizontal strips of the left matrix, transposing and storing it 2 tiles at a time. In the load section, we set up predicate counters for the first 4 lines. Now we use those predicate counters to load data into Z registers. Next we move those Z registers into horizontal slices of the ZA tile. In the store section, we're going to transpose and write the data to a buffer in memory. We set the PN10 counter for the first tile to hold the number of bytes in the highlighted area, or all true if more than 4 vectors. Similarly, we set the PN11 counter for the second tile to hold the number of bytes in this highlighted area, or all true if more than 4 vectors. In the next loop, the predicate for the first tile would be as highlighted, and the predicate for the second tile would be as shown now. Now we extract the data as vertical slices of the ZA tile. And finally, we write the data to the buffer in memory. We have transposed the left matrix data, which can be fed into the matmul code.